biggest is, because you're saying, well, it must be this number
really,
here.
for me, what everything is about in the computer.
Because remember, when we add
without
all those together,
understanding this concept,
that will always be
done a little bit
one
of
less than the
GCSE.
next column. So if you add those together,
okay, but without
you get
really
15
truly
going.
understanding what data representation means,
Okay.
you can't understand anything else in computer science.
So again, if in doubt, it comes
comes
up
down
in the floating
to
point
this
stuff as well.
element.
What is the largest negative number?
And
what's
the key word
smallest
is
number and all that? They
representation.
can ask you lots of different questions for that.
Okay, this is
You
how
don't need to know what the
use
number is. You can actually just write it in
numbers.
binary. So if they said in binary, what's the largest
Because
standard
everything in the
5-bit
computer is a number.
You could just put 0,
Everything.
1, 1, 1, 1.
So it's how we
What
use
would be the
numbers
largest negative number
to represent anything.
in sign of magnitude? It is
It's
just
what makes
that bit
computers
flipped,
very
isn't it?
good.
So it's the same magnitude.
At processing data.
So as a negative one,
Okay, and
you'd say
transforming
1,
data.
1, 1, 1, 1. And we go, oh,
I'm
that's
going to put stuff.
minus 15. If I was doing it in two's
But
complement.
what I mean by stuff is
So if
how
I-
we
I'll do the
represent
same,
numbers,
5 bits.
how we represent
2C.
dimensions, how we represent objects, colours,
They shouldn't need to say time
audio,
to complement.
images,
So in that, for the positive, the
molecular
largest positive number, what do we
distributions,
put?
everything.
Nope.
But it
It's got
all
a sign
comes
of
back
0,
to the
hasn't
same
it, again?
thing, numbers.
So remember, this is the
So
key
it's sort
thing
of
with
like,
when you're
a
doing
coding
the
system,
signed
data
numbers,
representation.
always start with
stems
sign.
From the bit.
And you go,
the
right, I'm going to put
basic
some column
unit
in
of
because I'm a
storage.
dumbo. So I've got 5
Anyone
bits.
know what it stands for?
But the column headings are sort of irrelevant.
Which sounds like a stupid question.
So I say if I've got a positive number,
Nobody?
I'm going to say, right, well, positive, I have to think sign
Yeah,
first. put
it's
the
one of
sign.
those stupid things. Binary digits.
Then I just say, right, well, using the rest of it, what's the biggest number I've got? And it's, again, plus 15.
It is the fundamental.
But with
building
negative,
block.
slightly different. Because we know,
The
unless
storage.
we're
So
not
all
clever, unless we
data
know what the
is gonna
system
involve
is,
bits.
we can't write a negative number down.
Okay.
So what
that's
we
the
do is we
fundamental.
actually perform two's complement, don't we? So we write down the positive version. And remember, this is where students really mess it up. They'll go,
What's
they'll
really
read
nice
two's
about
complement
it
in the question, and they'll go,
is it can
oh,
only
I've got to
have
do two's
two
complement.
values.
No. You
It can
only
only
do
be
two's
a
complement when you've
naught
got negative values to deal
Or
with.
a 1.
So if you've got
And
a
the reason
pattern of
that's
bits
really
and it
good
starts with the most
is
significant
because
bit
that
1,
can be
you know you've got a
represented
negative number
with
and you
a
go, oh, bugger, I
switch.
don't know what that is. Do two's complement and find out what the positive version is. Remember, two's complement is equivalent of
There is
like
no in
multiplying by minus
between.
1.
You can't like, oh, I
What's really nice about that
flicked
is
the switch and it
CPUs
sat in the middle and
have
it was
basically
either
got an
0 or 1.
instruction usually on most
It's
CPUs
either
to do
0 or
two's
1.
complement. So if you want to like
Okay.
flip the sign of a number,
Now,
you can just
building
go
a
bang, one
computer,
instruction, really quick.
we used
Okay?
to
So it
use
isn't like what we
something
do.
called
We have to
valves
do it all manually. That's got hardware
to
do it.
represent.
Right, so if I want to know what the
switch
negative
state. Valves
maximum
could
is,
be electrically
I do two's
switched
complement. So remember that
from one
involves
state
flipping
to
all the
another.
bits
And
in
if you've
hand.
ever been to Bletch,
But we've
anyone
got a
been to
short
Bletch Park?
way of doing that. We
The
flip the
Colossus
bits until we get to the last one.
Is a
don't we?
computer that's
So we go
built using
one,
valves. Because that's what they had
flip,
at the time. They're
flip,
actually
flip.
struggling
We get to the last one.
Get new valves to,
Hang on, that's
no,
gonna
not
probably
new
do it.
valves, but new old stock.
I'm going mad.
Valves to replace the ones that break.
no,
Because
no,
obviously
no.
nobody makes valves
Right,
anymore.
so
Um,
if we get to the last
ancient
one,
technology, really nice.
we put it as a
Uh,
1. So that is minus 15.
So in modern computers,
But
we
it's
don't
not
use valves. Anyone
the
know what we
smallest
actually
negative
use?
number, is it? What's
Yes.
the smallest negative number?
Transistors. So
Negative
valves is the
16.
old school analog
Now
way
let's
of
prove
doing
why
it.
that is in a sec. But
But we now use
this
transistors.
is the reason
now,
why
I don't
you can't
mean
necessarily write negative numbers down
transistors
straight
like you
away.
might find in electronics that look like that.
Because unless you know what the
Bits
system, I'm
of
not going to
plastic
tell you what the
with
system
legs
is.
on them.
All right.
Although
I know what
essentially
the
they are
system
the
is, but I'm
same
not going to
thing.
tell you. It's
We're
up to you.
talking about microscopic
You will see like
transistors.
explanations of how to do it.
Okay.
But yeah, that's
If you
minus
look
15.
at
You wouldn't
the
necessarily
current,
think that that was minus 15 just looking
state
at it.
of fabrication.
Okay, but if we was to do the
CPUs,
two's complement on
logic
it and flip it
systems,
back,
we are
then
now
we would.
currently producing
Now we said it's minus
hardware.
16.
So each one of these transistors
So what would minus 16 look like? So
is around, on
you
the
can't even
latest
write
stuff,
it, can you?
7 nanometers in size.
but it actually looks like this.
7 nanometers.
That's minus 16.
So that's the size of the smallest
But let's
components that
prove
we're making
what it
things
is.
up. So
We
all
do
the
two-
logic
it's
gates
a negative
made
number
out
we
of
can see.
transistors.
We look at the sign bit.
So and
It's
or
always
not.
about examining the sign bit.
Exclusive or, which is the one you haven't studied at
And we say, oh,
GCSE.
negative. can't read it.
NAND, NOR.
I know it's negative,
they're
that's all I
made
can
out of
tell you about it. So I'm going to do 2's
And
complement.
we can make these transistors very small. And
So
they're
I'm gonna go
still
flip.
created using photography.
But the flip process.
super,
Let's do it the
super
long way
accurate
first.
lenses.
Let's just go
So we make
flip,
a picture
flip,
and then we scale
flip,
it down.
flip,
We don't
flip.
zoom it up. We don't like
So that
do
was
a
the
projector
flip.
job. We do like a reverse projection.
But then let's
So you
add
take a
one.
really detailed image.
And the way that we add one,
and then you scale it down to
this would be
something
1.
about that size. And
This is
put
why we do
like
the quick
20
way of doing
billion
it. I just want to
transistors
show
on.
you it. Right, so we go 1 and 1.
Really?
And we go,
It
no,
is,
carry
it
1.
is
I know what's
scarily
gonna
awesome.
happen.
I
1
find
and
it
1
scarily awesome.
and no is
Let me
no,
do these
carry
things.
1.
Pure
1
math.
note and 1 is
Alright, so
no.
data representation starts
I've
with
got
notes
ones
and
and notes and you go mad in binary.
So the bit,
It's just like
as it
everything's a
stands,
1 and a note,
is
1,
useful
note,
to
1.
represent certain
Um,
types of data. Anyone
that's
think
how it's
something
easy to
that
mess
a bit
up,
could be
don't
used to
like it.
represent?
I don't know what they're testing, to
What
be
was
honest,
that?
but that's what they're testing. 1 note 1 is
Well, it
no,
could
carry
represent a
1,
number,
and then we end up with note, note,
but the
1 to
number
rid of
would
the
be
1.
limited to
So
0
it actually
and
looks
1.
like what we originally started
But
with,
what about real world things that it might represent?
which is a negative number, but we're saying that's 16.
On and off.
Why do we have that extra
Status of an
range?
alarm
Because the
that's
range
ringing.
on
Is it
the sound
alarm
magnitude
ringing?
is
Is
plus
the alarm
and
not?
minus the same
Are my
number. Why
headlights
do we get
on
an
or off?
extra value on 2's complement?
If you've got a Nintendo Switch, have I pressed the right trigger
Nobody?
or the left trigger? Because they're not analog, are they?
We're all done in the
Poor Nintendo.
Isn't it because
Go on, prove me
Anything where
right
there are
that
two
you are
states.
intelligent.
two's complement?
Okay. If you were doing some sort of catalogue of students and their whether they like cats and dogs, you could use
Yeah.
0 to represent a cat.
That's
1
the
to
essence
represent a
of
dog.
it. We can explain that
key
in
thing
we can show
is
it
the
physically
note
in
and
a
the
different
1
way. But yeah, so
isn't
2's
data,
complement,
it's just a way
the
of
number and the
storing
sign
data.
all merged together.
How we
Okay.
then interpret it,
So it's integral.
that is
But
what becomes
with
useful.
sign of
But
magnitude,
we have to decide
when we're writing a
what it
number, let's just do a
represents.
3-bit number.
Okay,
So this
that's
is
what this whole topic is
3.
about. I'm taking this slow.
this is
If you ever
minus
watch any
3.
data representation
So they're
videos on the internet,
separate
they'll-
bits,
they'll be
but
on
we
to
have this
stuff already,
anomaly
you know, within
because
2
of
minutes.
this,
They're starting
which you
to
just
go,
don't
"Oh,
get
this
in
I do,
2's
what do this I
complement.
do?"
That is
I want to take it
0.
steady. Okay, I want to build it up.
What number's that?
Okay, so it
Yeah,
isn't
which
the
doesn't even
0
make
and 1
sense.
that I'm interested
That's
in.
minus 0.
That is just how I represent. So,
So
no, it's cat,
that
1 is dog.
and you can
if
see
someone
that
else
that
comes
pattern
along and
is
says,
the
I'm going
one
to nick your
that ends
idea,
up
but
being
I'm going to
used
do
for 2's complement.
fish
It's
and
not like
birds.
penciled in. You go, oh, we'll just use that
And I
pattern.
could use
No,
fish
the way
for
that
one
2's
and
complement
birds for
works,
none.
the integral nature
But it's
of it, like
limited
Tilly
to 2
said,
things.
is just
So,
gives us that extra
yes, it's
representation.
useful.
Okay, which actually does cause loads
To
of
an
problems,
extent.
but it's actually quite
Real
useful as
world
well.
data is more
Okay, so
complicated than
that's
2
the
steps.
essence. You will get asked
You could,
to talk about
on
number
a time,
ranges.
have said
You will get asked
the
to
answer
talk
to this
about
would be,
minimum
oh,
values,
gender.
maximum values.
Male or female.
Right.
You couldn't do that
Let's
now.
talk about arithmetic
You
then.
couldn't do that.
So with if you get
It
a
just-
number
it
inside of
wouldn't be
magnitude
representing
and you're asked
the
to add them
genders
up,
that people want to identify as.
then you've actually got
So-
to take the signs away.
Don't,
So if I add
that's probably quite important for
5
the exam, that. If you ever get asked
plus
that, don't put gender down.
minus 6,
Because it wouldn't be stored as 2 states.
and I'm holding those numbers
Not
in
anymore.
sign of magnitude,
Okay? Because even if you...
so I would have,
if you notice when you fill things
zero-
in
let's
and they
just do it
ask
as a
you
full
what
bit
your
number.
gender is,
so I've got
and
0,
they'll
1,
either give you
0,
like a
so that's
big
gonna
old
be
list that's as long as a dictionary,
plus 5.
or they'll
And I
say
wanna add
male
it
or
to
female,
minus
or
6,
say I
so
don't
I'd end
want to
up
say,
with
or something like that. So
that.
so even if
You can't
you were only
actually
recording
just
male and
do
female,
that.
you still
Doesn't
would
work.
have a
You've got to
third
mess about
option that
with it
said
first.
did not declare or something. So
Okay.
that wouldn't fit in a bit.
Because it wouldn't make sense. If I decided
Okay,
that
so the
up,
bit on
what
its
would
own
the,
is
what should the
useful.
answer be? Minus 1,
It gets
shouldn't
more interesting
So
when
we
we
would
combine
expect the
bits.
answer for that to be 1,
combining
0, 0,
bits.
1. Alright. Right, so if we just add these together, so we get 1,
That's where we
1,
take
no, carry 1,
more than one,
no,
and we say,
carry
right, well, when
1.
we stick these together, we can
It
represent
doesn't
more
give you
numbers.
the right answer. It
So
doesn't work.
We can then represent more
So
things.
in order to actually process that,
And there are
you've got to
standard
actually
names.
examine the sign
So
bits,
one bit,
decide
so
whether you're
I'm gonna
actually
just put
subtracting
number
or
of
adding.
bits.
To actually means subtract 6 from 5. So sign of magnitude is no good for this. You can do it,
And then
but
I'm
it
going to
requires
tell you its name.
extra
So obviously
processing.
we know what one is because that's of the bit.
But if we write them in
That's a bit.
2's complement,
But there is a
we can actually
grouping
just
of
say, right,
4,
I don't
so
need to
put
even
4
look at the
bits
sign,
together.
I'm just
That,
going to
you should know from GCSE what that is.
So if I do 5,
Nibble.
5 plus
Correct.
minus 6, so I'm going to,
Nibble.
5 is the same, plus 5 is the same in 2's complement.
Nibbles are useful. Because
So
they
that's,
can
plus 5 two's
easily be
complement.
written in different number formats. And
But -6 I can't write
we'll
down.
look at the hexadecimal.
So-
We did it at GCSE.
And this is what
Most
you
people-
mustn't do. You mustn't do this on your exam
people
paper.
still
You mustn't
struggle
go,
with
right,
that.
I'm just going to write -6 down. here.
Hexadecimal
So I'm going to write
is beautiful.
6.
It's as beautiful as binary.
And then I'm going to do flip and add. So I'm going to go flip.
Right. When we
flip.
put
Oh,
8
that's
bits
the last
together,
one. Keep it the same.
we call it what?
Right, so that's -6.
A byte.
That's plus 6. If you're going to do this, show you're working out.
There are other classifications of groups,
Say working.
but they all
Right,
tend
so I
to
have
be
got
given the
that,
same.
but I just don't just leave
size
things
or the same
sprayed
name.
across a page with no
So
annotation.
these will be 16.
It's so important. The number of
32,
times I see
64,
students work, and you
and
think,
we tend
especially on
to
the binary
call
ones,
these
where
words.
let's say I'll come back to that in a second.
And I'll
You've got
explain
your,
why when we
your
talk
area
about
that you work in. Question was here,
Again, like I
and
said,
you've got like your lines, and you
last
see
week,
some binary numbers
all
here,
these
then you
things
see
cross
some binary
over
numbers
and they
up here,
explain
and then
each
someone
other.
does something down here, and
So,
then they go
but
back
just
over
take for
here,
now that
and they
anything
go
16
here, and they
and
go,
above
obviously that's the answer.
is a word.
It's there. That's the answer. But they don't
Can
label
anyone
it.
tell me anything that
You
obviously
mustn't do that.
stands
You've
out
got to try and
about
work
those numbers?
neat. Okay? So please don't do that.
Right, yeah. What sort?
Because
So
that
I
will
haven't got
make you come a crop
like
up.
7, or I haven't got 13.
Right. So going back, so I've got my plus 5.
They're
I've now
actually
worked
all
out
powers
what
of
minus
2.
6 is. So when I put
We
them
tend
together
to-
and add them,
Because the computers are set up this way, work
it should
in powers of 2.
magically just work. But it's not
Okay,
magic.
if you start doing
So I
other
get
groupings, you
1
start
and
increasing
0.
the processing burden. All right, so we stick to standard sizes.
1 and 0.
Right. So the
is
bit's the
1.
fundamental storage
0 and
unit.
1 is 1.
So if you want to store something on a
0
hard
and
disk,
1
you're going to
is
store a
1,
series of bits.
And 0 and 1 is 1.
You want to store something on an SSD,
And we know,
you
because
store a
that
series
is
of
the
bits.
number we can read in 2's complement, all the ones
You
is
want to
minus 1.
transmit some
So
data,
it works.
you technically
5 plus
transmit in
minus
a
6. It just
series
works.
of bits.
You might
Okay.
need to reform.
In a
If
long
you've got
chain, if you're doing serial transmission.
5 minus 6,
parallel
you might need to
transmission, you
rework
send
it,
a load
just
of
do a bit
bits
of
at the same
algebraic
time. And again, you'll see
changing
this in
and
action
say, oh
here
yeah,
with
that's
the
5
CPU.
plus minus 6.
The byte
What it
though,
actually means is you do not need
has got
to
another
do
important
subtraction
to us.
if you're using
when we're
2's
talking
complement,
about
because actually what you do is you just take
storage
the
in
second
memory,
value and you
it's
2's
what we have as
complement it
the
and add.
smallest accessible
So you just say, no,
address.
take the second bit, times it by -1, add it on. So you don't actually need subtraction. So you don't actually need to build any hardware on your CPU.
I tend to write
in
address
the
as
arithmetic and logic unit to
ADDR.
perform a subtraction
A, because
operation
I'm not
either.
lazy.
If
and
in the
B,
exam
because it's an acronym that
they
is
give
always
you
used in assembly language.
5 minus 6 and say, write these in
And that's what
binary.
I do a
and
lot
then
of. Smallest
perform
accessible
subtraction, don't do it.
memory unit.
You can do subtraction,
Obviously,
but
the-
I hate it.
You
I
can
don't like
access
normal subtraction, but
bits,
subtraction in
but
binary
the
is horrible.
CPU can't grab.
'Cause you have to, like,
from memory
borrow
one
from,
bit.
like, 5
It
miles
has to
away.
get at least a byte.
So always do
Okay.
2's complement add.
Or
They have to accept
technically,
these answers because
you
that's
do get
how it
full
works.
bit processors that only work with
Okay.
different.
Right. The reason the 2's complement
Next,
stuff is
super
important
specialist
is because of
old
floating point.
Okay,
Probably
so
your
when we
favourite.
talk about memory,
Floating
we talk
point
about memory
should
addresses,
be-
we're talking about addressing
Remember,
a
this
whole
isn't really
byte.
floating point. This is OCR floating
Okay.
point.
But we'll come on to that when we
Floating
start
point is
talking
not
about
like
those
this
things.
at all.
Okay, so once we get
So this is
we get
floating point
into the
OCR,
realms of
where we
sticking
have,
bits together,
and
we
again,
can represent more
keywords,
complex information.
Mantissa and
And
exponent.
we will get
so
asked
the mantissa is the detail.
by the exam board, how many things can you
That's the
represent with a
detail of the
number
number.
of bits?
What is the number
Now we did a
represent?
little bit of this at GCSE,
And this is the
because
size
you
of
got
the
asked
number.
about ASCII
Okay.
and
How
extended
they
ASCII, and they got
express
rid
it
of
in the
extended
exam
ASCII
is
now.
entirely up
All
to
the
them.
new things
They've
and stuff.
never not
But
used 2's
how many
complement,
bits
but they could turn around
was
to you.
ASCII.
So be warned. They could
Goes
say,
against what
"Oh,
I've just said,
the
7."
exponent is held in,
Okay,
Sign of
so
magnitude.
ASCII was 7 bits.
but they shouldn't do that.
The original
They might.
version of ASCII.
They'll tell you how many bits. In reality, single precision floating point is 32
But there
bits.
is a
But
form
because
called
32
extended
bits is
ASCII.
a
How
lot
many
of
bits was
bits,
that?
and you will screw that up.
8.
That's why they make this thing up. Okay? So they'll always have to tell you. I think, in fact, actually, there has been one question where they didn't do this.
Right, so
They'll generally always tell you
One
how
thing
many
the
bits for the
exam board will ask you
mantissa
to
and
do-
how many bits for the exponent.
they'll say, okay
And
then,
they'll say they're in
so
2's
given that
complement.
you've got a number of
So
bits
you need to be
together,
careful. They'll never give you a big
how many things
sizes
can you
for
represent?
anything.
So Can
The
anyone
only time they
remember off
haven't
the top
ever
of their
done
head
that
how many
is when they
bits,
mention
character
the
symbols
word
you can have with
normalise.
7-bit ASCII?
What does normalise mean?
128.
It's when you remove all the unnecessary stuff, it's like 1, 0.
Yeah.
You're on fire.
I'll show you the trick
You're right.
for doing it. Remember, there's no
Where we
calculator.
get
Even
rid
on
of
A-level computer science, you're not allowed
meaningless
calculator.
digits, effectively.
Even though you're going to
So,
spend
but why do we normalise? To maximise
the majority of your
what?
time working with the best calculator we've ever made. You're not allowed to use it in the exam.
Think a bit more abstract.
Right. How many
You're
for
still
8
going to use
bits then?
all the thing with these formats. You will use a
256
certain number of bits. You
items.
can't like say I'm only going to use 3 bits.
So
of
when
this.
we're specifically talking
because
about
you're talking about
storing
in general,
text,
a general
the
format.
item is called a character, isn't it?
No.
All right. So I'm trying to generalise a little bit. But I'm using them
Maximise.
as examples. Right. So
Precision.
how the hell do we work this out? Now you could go all maths nerd on me.
Maximise
and you could
precision.
say 2 to the power n.
Because we've
That's
got a
how many
limited
it
number
is.
of bits.
All right.
If we're recording
So,
zeros,
you've got no
or things
calculator.
that don't make any
So that's not going to
difference
necessarily
to
help
anything,
you.
then
but
that's
it might help you
wasted
screw it
bits.
all up and get a
All
random
right.
number.
How can we
But
see
actually,
if a number's
the
normalised?
best way is the dumb way. So we're going to spend computer science, and I'm going to show you the dumbass ways of doing things.
Yeah.
All right?
First 2 bits.
Because
are
dumbass
different.
ways are easy,
It's the dumb.
and
way
they
of
don't take
saying
much
it.
remembering. I could take you through the
So we have
convoluted,
got-
complex ways of calculating everything.
For a positive number, they
They
should
make you
all
heroes
start.
on
And we're
the
talking about
internet.
the mantissa here.
But you ain't going to
So
have
we remember the
access
binary
in a
point
computer exam.
is
Right?
implied.
So we're not going to go there.
It isn't
Right,
actually
so
there.
when I'm
How are
grouping
you gonna
bits
represent
together,
the point? You're not going to store
I'll do
that.
the 7-bit
So it's
one. So we're
implied
going
that
to
it's
do
after the first bit.
7 bits. So let
that
me write
doesn't
down
exist,
a
but
binary
a number,
pattern or a
if it's
bit
normalised,
pattern as we call it.
always
So this is a
start
bit
positive,
pattern.
not 1.
Loads of technical words.
it's negative,
loads of technical language that we need to get
It's
used
going
to
to start
using.
obviously
So this is
1,
the bit
'cause it's
pattern.
negative, but it's going to go 1.
And it's
not.
going to be
Which
a
again, when you look at it,
peculiar
you think,
bit
oh,
pattern.
actually, it's in 2's complement, so don't worry too much about it.
It's going to
So
represent a
that's
character.
how you can spot it.
So, I'm
So
gonna
the only time
represent
they never
this as a
ever
character. So I'm saying
said what the
this
mantis
pattern
was
of
point
bits
on was where they gave
is
4
a
numbers and they
character
went,
value.
which
it
one's,
could be the number
normalised?
of oranges I've got in my fridge.
and you had to like look at it. They were
Why I'm
testing
keeping
whether you
oranges
knew
in the
what the
fridge, I
hell.
don't know. And why I've got
That
that
bit
many, I don't know.
The
Okay,
one
some
and the
sort
naught
of
and the
freako
not and the
orange. Maybe I've got an orange juice
Okay.
factory, and I need lots
Right.
of oranges.
So
in my
there's
fridge.
2 tricks.
Because I wanted
they
to
might
work on
ask
it
you
today, but I
to
couldn't
add
do it.
up
So I
floating
waited
point
to get home and I
numbers,
wanted to
which is
refresh.
probably the hardest thing they can get you to do, but it's actually
That's a
trivial.
good
but
example
it comes
of
into
our
everything
ramble
else.
Sorry
So
about that.
let's just
Right,
go
so
through the process.
Can
So
anyone tell me what
one
character
thing
that
is
is?
being able to write decimal number in floating point. So decimal to floating point. So
No,
let's
that's
have
the
a number.
value.
They'll often
That's
these
just
are
what
normally
that
be
binary
simple
value
numbers.
is. You're right.
You've got no
You're right,
calculator, so they
66.
can't like
That's good.
go represent
But
pi.
the question
in floating
was,
point, or
what
anything like
character?
that. It's always going to be some sort of power of 2 fraction. So let's go for 3.75.
Anyone remember what capital A was? But you don't need it.
And
You
then
don't
we need to
there's a
decide what
dumbass way
format.
of
So
doing
let's
this.
go 5 mantissa bits, and let's go
There's a dumbass way.
3 exponent bits.
Right.
So we've got an 8. We're using
I'm
8
going to do
bits,
this
and we're
first.
deciding how we pack
I am
it.
going to assume that I'm
Okay.
stupid
Right,
and I
so
can't
our first
count,
job
I can't double in my head.
Is we look at the
By
number
the
and
time I
say
get
is
up
it
here, I'm
positive or
going to forget.
negative.
So what I'm going to do,
Positive.
that
isn't it? Right.
is
We're
the
going to write down a
one
0
column. That
to force it to
is
be
the
positive.
2. They get.
So
This
we've
is
only got
binary,
5 bits.
Base 2.
So let's do
So the column
1,
that we
2,
represent
4,
with the digits, the
8,
bits,
16.
are
Right, 5
all
bits.
powers of 2.
Well, let's just write
Going
down
on. So we go 4,
3.
8,
So we got
16, 32,
But
64.
we want to be able to
1 to
put
8.
down 0.75. So just in the same
How
way
much
that
is it?
as
I
we
don't
go
know.
left, we double each time. As we go right, you can see
Okay.
8 becomes 4, 4 becomes 2.
So
1
that
becomes
is
half.
my column headings. Anyone
it's
know where those
quarter.
column headings come from?
Then it's
Let
8.
let me write.
then it's
16.
then it's
32nd.
then it's
Right. What number is that?
then it's
128.
Yeah, you're annoying me now. I thought
Can
he was gonna
anybody say
I
how
thought he was going to do a
Pretty
pretty
Patel would
Patel
say
and
it?
like do that. You know when she read them numbers at that time?
700
She
T's,
like that
60
406,000
or something like that. she'd say.
273, and she couldn't say
She
it.
can't pronounce numbers.
It was like umpity tumpity tumpity
Right.
bumpity.
So
Uppity
is everyone
bumpity
agreed that
bumpity.
that's
It was like
762?
3 million and
Why is it
1,065
762? Why isn't it
and
267?
29 million or something like that. It was disastrous. But anyway,
Right, we've got column ends, haven't we? That
Right.
actually, because
you
you've
can
done this
put
so many
as
million
many
times,
bits down as you want when
you
you
just
first start.
accept what the column ends are.
I've just made sure
So
I've got
you
the
say,
positive in
well, that's the
front.
one
So I could have
column.
like
What's
put
the
more
next
bits.
one?
Because I don't
10. I'll
Right,
get
so I
some
want to do
square building
7.5.
blocks
So
down.
7.5, and this is where you need your maths power.
I
Half
always
and
used to like
quarter
them at
to make
school, where you had
7.5.
like
Yeah?
the lines of
Right,
10.
so all the rest is
and you could
zeros.
get 10 of those, stack them, and then you had 100.
So we write it down first.
Right. Where do those
Then
column ends come from?
we need to normalise.
Powers of
So
10.
normalise means that we have
How do we
one
get
sign
one?
bit and then we go
And
straight
notice
into
something
detail.
weird. Binary
So the
starts with
sign
1
is
as well.
positive. So currently the binary
is 10
point is
to the
there.
0.
So this isn't normalised.
This one.
Okay, because we've
is
got
10 to
sign
the
bit,
1.
sign bit, sign
This
bit.
one
So basically
is
what
10
it is,
to
we
the
want to
2.
get rid of the duplicate sign bits because
So
they're
in
wasting
binary, same
columns
thing.
that
The
we
10
want to use for
here in
detail.
decimal.
So
Everyone calls
we
these
want
decimals, don't they?
the change
That's
to
not,
be there.
it's deanery.
That's where we want the binary
The
point.
base
So
is
we do
deanery,
the shift, and this
right?
is
And the
important because
example
this tells
will
us
use
what
the
the
term
exponent is.
deanery.
So we go move
Decimal
it
is
one,
something completely different.
and I recommend you do this
But
because they
humans
will
get
want to see
trapped into
how,
using
whether
the
you
wrong
got
terminology all the time.
the initial
It's like everyone
place
calls,
correct, and you might get a mark
says,
for that, and you
the
get a mark for
internet when they
shifting
mean
it
the
to the
World
right
Wide Web.
place.
Everybody
So
says
we
the
moved
internet.
it 1, 2
Everybody.
positions.
Apart from
and
me, I
that's
don't.
where
I'm
we
not
put
an
the binary
oink.
point. So even though I've actually got
The
confusingly
media
two
call
binary
it the
points written
internet.
down,
They don't actually know what the
I've
internet
put the
is. That's
arrows
just a
on
set
and
of
I've shown
computers
that
are
what
linked
I've
up.
got is
The web is an application that
um,
sits on
a
top.
movement.
That's what they're talking about. The
Right.
web.
So the magnitude of the
Right.
exponent
So
is
these
how many
are base
places I moved
2.
it. So the
this
magnitude
one
is 2.
2 to the
But
0.
is it negative or
this
positive?
is 2 to the 1, 2 to the 2,
Now,
2 to the 3.
It's
2
easy
the
to work
4,
out because actually we've
and
made
so
that number smaller
Okay.
than what it originally was.
This is
haven't
actually
we?
quite
So
important.
if we just write that out
because
again,
when we're
so
describing
we only
a
want 5
bit
bits, we only have 5, so
position,
we've got the
we
0,
refer to its
then we've got
column.
the 1,
So the 1 on this right hand side,
1,
this one is bit 0.
and we've got a number that is now less than
Get
0.
used to everything
Less
in
than
computer
1.
science starting at 0.
So we've actually shrunk it,
first
we've
thing
made it
isn't
smaller. So to get the
1,
number
it's
back,
0. So in this
we
case,
have got to
it's
make
0.
it
But I want you to
bigger.
understand why.
so
I
that means the
refer to that as
exponent
bit
needs
0.
to enlarge
So if I say
it,
to
so
you,
it needs to be a
what
positive
is the
exponent.
value of
And we've said
bit
it's 2. So we can write our
6?
exponent down
What would the answer be?
as that. If you get stuck in the
1.
exam, just think
Okay,
scientific
Bit
notation.
6 is that one.
Or
Because this one is
exponential
bit
notation,
7.
or whatever you
This
wanna
one
call
here
it.
is 2 to the 7.
If we've got a
That's
number
2 to the 6,
0.79
that's 2
times
to the
10 to the 10,
Okay.
that's bigger than that, isn't it? So positive
you're not-
means make it bigger.
You know, you're
We've
not
got a
going to
number
get
that's
asked
smaller than
directly
what
that
we're
by
writing
the
down
exam
as.
book, but I
if
want
we
you
put
to
minus,
understand,
we actually mean
'cause
make
it's
it smaller.
fundamental to everything.
So when we've shrunk a number to normalise it, the exponent is always positive. If
Okay,
we have
so
to go the
back
other way,
to the original question.
then
You
it's gonna be
said
negative.
that value,
So let's do
and this
one
is
that does
really, really important.
and then we'll go
That
backwards. and we'll do
number
the-
does not mean
point-
anything.
point
It's
back
not
to
a
the-
number. It's just what is that?
So
value?
let's have a number.
It's got
So a
the
number
value 66. But
that
it's
is going to be a
actually
negative
capital
exponent.
B.
It's going to be something that is already less than, well, less than half. So let's go for
Okay. If I do this,
0.125.
right, this is one thing that I'm going to really
Let's
be
write that
cross
down.
with you if you do.
Now I'm testing your powers of maths.
If I turn that into a 1, why would I get cross with you for doing that?
All right, if you're going to get like that. Well, let's have.
Yeah, you've now got an indeterminate bit, which we can't have. So
I
you
was going
never
to do
ever
a 6125.
scribble out
Right.
or put lines
0.375.
through a 0 when you meant to put a 1.
Right, that's
Ever
3
do
eighths.
that?
So
Cross
let's
through
put
an
some
whole answer
column
and
headings
write the
on.
thing again.
Now we know it's positive,
And I will be.
but let's
brutal.
just go
If
like
you do a
one. I'm
test
just going to go
and
1,
you
2,
Do
4,
something like that. I'm going to give you 0.
and
The
whack
whole
in my.
question. I don't care
positive
whether
sign.
you've answered the rest of it.
And then I'm going to have to
be
obviously.
horrible.
I'm going to need to go.
All right. So don't do it.
Do I
Right.
need to go beyond an eighth?
What character is that
No.
now?
So
Now
I
I've just
don't want to
changed
waste
bit
too
5
much
to
time
1.
doing it. So I know I've got no
What was that?
2s, no 1s. I'm not going to get a half out of that. So it is just
I have added 32 to the number. What characters that now represent?
what you can do, and what I have advised students to do before, is that wherever you start at, double up.
So that
the
is now
numerator.
little b.
So you can like say, oh well, that's 2/8.
Very interesting.
4/8.
What that
It
means
depends how
is
dumb you are.
that if I am
What system?
trying,
I
you know
always,
when you
I
like
always
sometimes
work
you want
out
to change
work
the
from
case,
the principle that most
you want
people
to make
are really
something
dumb.
uppercase or lowercase,
Um,
I can
and they
do
want
it
simple
by
methods.
toggling
Simple methods
bit 5.
don't
I only
involve
have to
things
change
that will
one
really
bit
get
to turn
complicated and
something
cock up.
into an uppercase or lowercase or a big version or
They
little
ju-
version
yeah, they
of
are.
a character.
You know, overcomplicating
Okay,
something.
so-
You're asking for something to like cause problems. Right.
What
so
you've got to remember is
we've got that. We need to
when we
normalise
first
it again.
started
So
programming
currently,
computers,
so
they've
don't ever
always
cock
been
this bit up.
fast.
Make sure you put
Okay.
the initial binary
Well,
point in the right
fast-ish.
place.
Um,
Right, so
computers
the
that I
binary point,
program have
actually, we've got loads of leading
clocks
zeros
that are
there.
one-
So we
about
need to go
1.5
this way.
megahertz.
So that's where the binary point needs to
Okay,
be.
so that's quite fast.
So
That's
we're gonna
still
go
like millions of cycles a
that way.
second.
And we're gonna
but
put-
nothing compared to what we're doing now. So you wanted quick ways of doing things.
If I
So
drew
if you
some
need
eyes
to
on there,
change
some
the
hair,
case
it'd
of
be
some
clown, wouldn't it?
text in a document, all you have to do is change a bit.
Yeah.
So you didn't have to
right.
do any
So we've
process, you
moved
just have
it
to change the bit.
1. So the magnitude of the exponent is 1. But let's just
now that
write
we've
down
got
our number
a load of
so that
bits
we can
stuck
see. We've got
together,
5 bits.
we can
We
represent
actually
more
only
complex
got
data.
3 pieces of information. What do we put in the other 2?
Tends to be that we don't mess about with things
Yeah,
bigger than
zeros.
bytes in the
So
exam
there's our
stuff.
mantissa. Now, so we
Alright,
got
but
magnitude
how
of
we
1.
use those bytes,
So we
well, that does matter.
actually, what
But it
number
isn't
have we
about
got there? If we just look at that raw,
What the
as a bit
number
of
is.
fixed
The
point
number
binary,
is just
what
a number. That's
is
just
that?
our way of looking at that. To the computer,
Yeah,
it's just a load of
it's
noughts and
bigger,
ones.
isn't it? So it's too big. So we need
We
to
don't
shrink it.
like noughts and ones.
So
because
when
they
we
make it
do-
three.
Our exponent,
So
we
we
go, right, we've
still
got 3
like
bits
working
minus 1.
binary.
Well, actually, we're experts at 2's complement, so we know minus 1 is meh, meh, meh. Okay? And that's it. Right, so nothing
so it
complicates
helps
so
us.
far. When
You know,
everybody
so
like throws
You
the
might
toys
want
out
to
the
remember
pram
that with ASCII,
and like goes,
65 is
do
capital
what?
A, little a is
Or
97,
wait,
but you
what?
don't need to remember
Because
little a.
when someone
just add
says,
32 to
write
it.
down a negative number in
Yeah.
floating point, and everyone like starts wetting themselves. For some reason.
Because how they've
I've
laid
never
out the
understood
coding
why.
for the numbers.
So let's have a go at minus 1.25.
Yeah, so where capital Z ends,
some column
then
ends
you've
down.
got a bit
Let's
of
go
spare.
1, 2. I don't know how many I'm going to want.
Capital Z, if I
Load
remember
in.
right, is like 90.
Oops.
Okay,
What
so
have I
you've
done
got
wrong?
like 6 characters
forgot
where you
that.
just wedge some characters in
I'm
there.
stupid.
Alright, so you don't waste the space, you just wedge some stuff in there.
Quarter.
Now they've done it specifically
Pardon, Richard?
so that they could do this
Don't think
nice
the microphone
quick
picked that up?
coding of the upper and lower case.
It's a good job they can't
Okay,
see
so
me shaking
that's
my
just a little example of it.
Because I am shaking my head.
So what
listeners.
the exam board will say to you
I'm rolling
in
my
more
eyes as well.
general questions, they'll say, okay,
Right,
then
okay,
I'm
so
going to
we-
give you 5 bits.
What's our first
They're
problem?
going to say 5 bits. How
It's
many
negative.
different values can we represent?
2's
with
complement,
5
negative.
bits? And you'll
Ah, but when you're doing integers,
I know my maths. It's
what
2
do you
to the
do?
power 5. Okay, and then you go, I haven't got my calculator, I can't do that, I'll mess it up. So all you do is
Nope.
you go, right, okay, I'm going to put some column headings down. I'm going to go 1, 2,
No.
3,
No, because I can't write it down. that
4,
way. What was you going to say,
5.
Tyler?
That's really hard.
Yes.
Right, to say a number outright.
Till he's
It's like those
showing you
things where
all.
you get those psychometric
usual.
testy things where they have a colour
yeah,
and then
I-
a colour
I'll write
and
down
writing in
plus
different things. So they have
1.25
green, but
then.
it's in orange. And, it's
And then
like,
I'll do
"Ooh,
2's complement
it's
on it.
ready."
Right.
That's all we
so
do. I've
let's-
written down 5
you
bits.
Don't, it doesn't affect
To
the
work
exponent
out
at all.
how many
The
things I
exponent
can
is just the same
represent,
calculation.
all I've got
How
to
many
do is write
places
down
do we
what
move
the
the
next column
point?
would be. You've got
So
to
yeah,
do
let's
that.
write down plus 125. So we put, which is what you were saying, Dara, though, we put a sign in, but we have to put that positive sign in because
Right,
write down
so I
a positive
just put
number.
the 32.
So we go, right, okay, I
Hey,
can
and guess
probably
what?
do this.
That's how many
1.25, none of
different
them,
values
I'll
you
have
can
one of
represent
them,
with 5
none of them.
bits.
So that,
that's
and
a
again,
dumb,
whenever we're doing the
quick
2's complement,
way
make sure the examiner knows that
Of
you haven't
doing
got it wrong,
anything
you're in
like
the
that.
process.
What if they said to us
So
12
we're saying
bits?
that is 1.25
See if you can work it out
plus.
before I do. So 12
Then I just do
bits.
2's complement on it.
So just start
And I'm
with
not
the one.
going magic, I'm not doing anything magic. I'm just doing the same thing. It's just a pattern of bits to me. The fact that there's a binary point there, I don't care about that. I'm just going to do 2's comp. So I'm going to go flip, flip, flip. I'm trying to be clever and do it quick, so I'll cock it up. Flip. Flip. The very last one, keep as a 1. Everything else should then be a 0. If you don't find that everything else is a 0, then it wasn't the last one.
4096.
Right.
Has anyone beat me?
Right, so that is now
You got close.
minus
Close but no cigar.
1.25.
Yeah, so with 12 bits, I can represent
We've got to normalise it.
4,096 different values.
So we look at
that's
the game. This
one
is
thing we're gonna
identical
ask
to
you
the
to
one
be
we
able
have
to do.
previous, but this time the sign
Okay.
bit's 1.
And it
So
should
we've
be a
actually got
no-brainer. You
multiple
shouldn't make a
sign
mistake
bits.
on those
We've
questions.
got, we're getting rid of the
The
sign
other thing
extension
they're gonna
effectively when we
say
normalise.
is
So
what are the range of
I don't
numbers?
need that, and I don't
What
need that.
specific
They're
values?
irrelevant.
But
I
we
want
can't- we've
it
got
to
to
go
stop
1
straight
that
away.
is
No,
negative.
stop.
No.
Because
So
it matters
actually, I've got to
what
move
we
it
mean by
that
numbers.
way, and it's going to end up there when I normalise.
Numbers are weird.
Okay.
We
so
store
I'm
numbers
going
as
to go
humans
now
in
and
different
write down the
formats.
5 mantissa bits.
So in order to do
one
that on a
sign bit,
computer, we've actually got to tell the computer what
Point
format
naught
we're using, how to
one
interpret the
one
patterns of bits to
zero.
represent different numbers.
that's my mantissa.
Anyone give me any
Right, the
number
magnitude
formats? Any types
of
of numbers
my-
that we use as humans? What's the one that you learned first about? Integers.
the magnitude
We do not
of my
spell
exponent is
integers
1 because I moved
like
the
this.
binary point 1 position. But I have
might
shrunk
say it
this
like
number.
that.
So I need to
Integers.
make sure that when
We
I
might say- we
unnormalise
might
and
spell
get
it
my
in a
original
northern way,
number back,
but in
I
integers.
make it bigger. So that's going to be plus.
Alright. That won't go down
One.
well either with the exam board. Right.
The other thing I
we
would
have
say,
to
which
get
I haven't
technical
done on
words
any
correct.
of these, is I would just make it
Even though
really
I'm the world's
super clear
worst
that that's
speller,
the exponent
and you'll be able to test my
and that's the
spelling
mantissa.
skills
If
all the way through
they're
this
being
course,
really
and that'll be good
niggly
because
and
it means you
picky,
can spell it.
you mustn't write the binary point in your
So
final
we
answer.
need to make
If
sure
they're being
we
picky.
say integer. Right, so that's
they
one.
could be
Anyone know of any other number formats?
Right, so there isn't anything scary about
Right,
the negative
okay, this is an
floating
interesting
points.
one. Float.
Right, the bit
It's
I
actually
find that
floating
that is
point.
harder than going backwards. Going from floating point
Is what it
to
represents.
decimal
Float is just a
representation.
short term we use
So
when we're
let's have a
coding.
look at that.
Okay, for a data type.
So I'm gonna
Actually, it's got another name.
write down this first.
Floating point.
I'm gonna use the same format.
Floating
5
point
mantis,
is the technical way that we can represent, but there are lots of different ways. We actually call it a real number.
3 exponent.
A real.
Right, what can you tell me about that
It's,
number?
it's
There's two
interesting
pieces
because
information
most of
to
the
tell me about that
programming
number.
languages use the term float, unless it's Visual Basic and it uses the
It's
term
not
single.
normalised. So whoever
That's
wrote this
Visual
as a book,
Basic to a T.
what else can you tell
Um,
me?
the exam board were obsessed with. No, we need to keep it abstract, and it's a real number. It's got fractions.
Right,
it's a real
the
number.
exponent's negative.
And they've actually
What does that tell
conceded
me
that
about the
everybody
actual
knows
value?
it as a float, which is why you said float straight away.
Yeah,
Okay.
so it's going to be less than
Right,
1. It can't
these
be
are not
bigger than 1.
Individual
We're
formats.
gonna
These are
shift that,
groups.
Make it smaller.
We have subgroups within all these
Right.
things.
It's not
There
normalised,
are
but that doesn't matter for the process.
others.
Normalisation is just making sure we
Fixed
maximise
point.
that precision. Doesn't mean we don't
When
sometimes
I wrote
hold
my
numbers
3D
that way.
game engine
for various
my
reasons.
degree
So we're gonna
project
go
back
through
in 1990,
the process. So the first thing I do
I was using a
is
CPU
I look at my
that
sign
didn't
bit
do
and I go,
floating point,
hey,
only
it's
did
positive.
integers.
So no matter
So
what
I
I
had to
do
make
later
a
on,
fixed point
I can double
format
check. So it's a positive number.
When I was writing it all in the
I
same
then look at the exponent.
Fixed point's good. It means you've got a
It's 2's complement.
position
It's a negative
where
number,
you
but
put a
actually
binary
we know
point,
what this is going to be. So
it's
what's this
binary.
exponent?
and then you
gonna
say
be?
there are a number of bits for the integer bit and a number of bits for the fraction bit, and it's rubbish. It was really
Minus
good.
4.
When I first started doing my experiment,
I'll-
if I
we'll prove it in a
rotated
sec.
an object, a cube, 360
So that's my
degrees
first job.
and
I want to
stepped
know
up
what
like 5
overall that
degrees,
number is. It's
by the
positive
time you
number.
rotate
And these,
once,
if they
it
said
was
without
looking like a pyramid.
telling me what this number
Because
is,
of
what
rounding
is
errors.
it? What can you say? They're the
Quite
things that you
hilarious.
can say.
You couldn't do
Okay.
rotation.
Right. So the
That
exponent's
happens.
negative, so it's going to get
Right, fixed point.
smaller.
There are others.
By what?
We don't need
How
to
much
know
are we
about
gonna
all these,
be
but I want to give you
dividing
a
that by?
flavour. Okay? BCD.
Because every time you shift, remember you're dividing.
No, it's not some sort of sexually transmitted disease involving computers, which there may exist, those things.
16.
Anyone know what it stands
Divided by
for?
16. Remember, if you shift
It's actually
right,
a really cool
you divide
format
by 2.
that
So
a
if
lot
you
of
do that 4
CPUs
times, it's going to
natively
be 2 times 2 times 2 times 2.
support.
Yeah. Right, so it's going
It
to get
actually
smaller.
stands
So
for,
what
it used
I'm
to be
going
on the
to do
syllabus as well.
is
But
I'm
it is
going to
actually useful. Binary coded decimal.
put my binary point in. But if I'm going to make it smaller, that
one stands for
binary point's got to go that way.
binary
hasn't it?
coded
So
decimal.
I need to pad
It is a
with load of
way
leading zeros.
of getting
Put as
round.
many as you want. I know the
floating point
exponent's
problem.
4. So,
So
actually,
you may have seen,
I'm only going to move
if you
places,
did any
I'm just gonna go
database, anyone do any
crazy.
databases? We didn't.
Right,
we
and then I'm going
avoided
to move
that.
it.
So I made sure you
So I'm
didn't do
gonna
any
go
databases
1.
because it's not interesting.
2.
But anyone at the girls' school do
3.
databases?
4. Oh, you click that
Did you ever
button on
set
there.
any data types to currency or anything like that? Yeah.
That went miles.
So when you actually set currency, what you're using is
Sorry,
binary
everybody.
coded decimal form.
Who's, well, if you're still awake.
Right, let's
Right.
focus on the two that we have got to really drill down on. So that is, so these are all numbers.
There's a switch on
So,
the pen.
but when
What
we're
we
as
do.
humans, we say, oh, numbers.
Right,
this is
okay,
a
so
number,
that's my number.
762. If I want to put some decimals,
This
I'll
is
whack them
interesting.
on.
We've
Well,
only
make it
got-
negative, I'll put a minus in front of it. If I want
We
to
can
write
work
it down
out
in
what the
scientific
number is,
notation, I might
but
do something
actually
like
we've only got
this.
5 bits. That is my sign
Might
bit.
It's just a number
Isn't
in
it?
it. It's a number in it. In it. And everyone says in it.
Naught.
It's a number in it.
Then
Obvious.
I've got the binary point.
It's obvious.
And I've only got 4 more bits.
But no, it's not. Because we've got to actually figure out a way of storing this thing
That's why we
that can be
normalise.
stored and then can be processed
That was
later.
partly normalised, not fully normalised, but it had been
So,
moved around.
Let's
So
focus
if we
on
were
integers
only
first.
using 5 bits,
Right,
when we
I've said integer is
unnormalise,
a
we're
group.
effectively unnormalising the number so we can find out what it is. If we was to only still use 5 bits, we would lose anything that
How
was
the hell
smaller than
can
1. We'd
integers
lose
be
the
a group
detail.
when it's just
It's
whole
gone.
numbers?
We actually we're assuming we're
Can
representing
anyone
it as
give
0.
me 2 types of integer?
This is a real good example of floating point. This is the problem with floating point.
Right.
You don't hold
Let's
things
play handball.
precisely, and when you start using those numbers, because you
Right.
have to add them
What
together, you have to
you-
unnormalise.
Right,
and things
you
like that,
will
and mess
call
about with
this
the exponents.
binary. Alright?
Once you start doing
binary.
that, that's when you get
So
accuracy problems. Remember, precision
This
is
is
about
what everyone
holding the data.
else calls binary.
Accuracy
This
is about
is
using
binary.
the data.
That's your
You
clip.
get rounding errors
Right, hang
of
on.
accuracy.
This is where you find out how bad my spelling is.
It's probably one of the hardest
Because
things
I
to
can
try
win
and
at hangman by
explain
spelling the word wrong.
When, if you get to say
You
what is the
can't
difference
guess
between
it.
accuracy and precision. Precision is
I have to-
holding
I have
the
to
data.
see it in my head.
Accuracy is using the data. Right, so, but obviously we're not, because we're unpacking this. Then we're going to
Right,
keep going.
okay,
So
give
we've
me
got
that.
1, 2,
You
3,
can't have
4.
vowels.
We've got another 0.
You can't have vowels because that makes it too easy. No, I play advanced
I used
hangman.
to set
No
questions
vowels.
for my A-level one, and
Right.
I used to give them like 6
This is why you've got to do
exponents
that
and then
thing.
make
No,
them
you
massive
can't have a word with all
numbers.
vowels.
And then say, what's that number? And I
C.
used to get like
Excellent
daggers
choice
thrown at me
for the base.
for doing it. Because now I want to know what that number is. I've got to go, right, well, I'm not going
P.
to bother. I know
That
it's less
sounds
than
on
1. So I'm going to
paper
go
really
half,
good, but actually, that's
quarter,
a very sturdy fold.
8,
Right, another one we shouted out.
16, 32,
D.
64,
I thought you said
And I'm gonna
Z
go
then. I
1 to
thought I was
8.
in America.
and then I'm going to go 2, 5, 6. And again, this is if
What
generally
did
they
you
won't
say?
ask you to write the
Oh,
answer
well
in
done.
decimals. Say what is the answer.
Unsigned.
Okay, so that you could leave
Everybody
it like that,
calls this
theoretically.
pure
But
binary.
again,
or
if you want to be able
binary.
to add that up easy,
Unsigned.
that's when I do
Now,
the thing. So
what
I go,
does
oh,
that
that's
mean
a 2
then?
and a 4. So actually that is
yes,
7.
only
2,
positive
5, 6.
numbers. So for integers,
That's what that number is. That's the power
what everyone
of the
else
floating
calls
point.
binary or pure binary.
So in 8
or
bits,
whatever,
we've been able
we
to
have got what we
represent
call
quite
the-
a small number. But we can't go. I mean, that was the
Unsigned
maximum
integer.
negative number. Okay.
Unsigned.
Maximum
So that
negative.
is only
I cannot.
positive.
So theoretically,
Right.
the smallest
Just so you
number
know,
I
I don't
could
like writing the
actually
word
write
positive. It's too long.
would
So
be
I do.
with that unnormalised.
Charming.
So it would be something like
I'm only trying to teach.
no,
They could do that another time.
1.
Only positive.
With that, so it'd be 1,
All
2,
this is
5,
captured
6.
on the video.
Would be the smallest
Positive. So I'll put
positive
a
number
plus
I can represent.
VE.
What's the largest I can represent?
When I was in
would you write?
what
What
you
would
would
the
call year
floating
10,
point
but we
pattern
called
be for the largest
year
positive
4.
number in 5-bit
Yeah, I think it's
manticula,
true. So,
3-bit
but this is
exponent.
all confusing to me.
What would the
Um,
exponent be?
We did O-level maths, which is what you call A-level maths now. But there you go. And we
Don't
did it in
start
a year. and we
incrementing
had a
them
really
until
good
then.
maths
You let me
teacher,
down. You let me
and
down.
she was the one that was really brutal.
It'd be 3, wouldn't it?
And said
If
like,
you're going to keep going.
if you don't,
No, I meant like the start.
Oh!
and the time.
Hang on, I'm going to have to...
I was
We
a
can't
bit
do that while
confused.
we're talking. So yeah, she was quite
Right.
brutal.
The only other thing,
and
which I think
at the
means
time,
making
we
you
all
adult
thought she was
floating
just
point
like
numbers.
some
I don't know what
crazy
they're testing.
woman.
They ask you about normalisation.
But actually, everyone
it
in
on
the
normalised
class
number.
got
Fine.
an A, which was the maximum
But
grade
don't
you
then
could get. So
make
30
them add
students, we all
the
got an
integers
A
together.
because
Because
she
it's just
meant
intuitive once
she
you've
would make us in
normalised.
our
So
books.
if we've
we
got
had
two
to
numbers,
draw a margin
So
in our
arithmetic.
books, and it had to be 1.5
so everything else
centimetres.
that we did for
I
integers
kid you
is
not,
the same.
and she measured them.
All right, so if you've got to say
1.5 centimetres.
if you've got,
you
I'm not
had
going to do this one, but if you've got
underline the
1.75
answer,
minus
and the lines had to
0.25,
be in alignment.
you can
so
actually
you couldn't
rewrite
do
that as
this.
1.75 plus minus 0.25.
And if you didn't do a
Exactly
margin
the same
and you
process.
didn't do that,
So if you can do
and you didn't
integer
line
addition
everything
and
up,
subtraction,
you got
you can do floating
nothing.
point.
Whether you got a question,
Right,
this
so
is
let's
like,
do
that's what she did.
something that we know what the answer is.
And when we were
So I'm
learning
gonna do
things like
1.5
trigonometric identities,
plus
so like what
2.25.
is sine times
What's the answer
cos,
gonna
and
be?
what does that turn into, and how can you
Yeah.
refactor
So the
and
answer,
everything?
this is why I always
made
like the
us
binary
learn
questions,
them.
because you actually know what the answer is.
And she would say,
So
she would
if
say,
you've
come
completely
on, it's a
gone
look and say,
crazy,
it's a look and
you can
say.
at least get
So
one
she
more
made us
for
like,
the
we had
final
this
answer.
page of about 100.
But that's
we
why
had
they
to
always have to show
memorise
you
them.
working.
Because
So the first thing
actually,
we've got to do
and you think, oh my god, this is a nightmare.
is write
I couldn't
those
do it
down.
now. My brain's
So
gone.
I'm going to go,
But it was, she was making us do
and
that.
I'm going to write them
so
down
that
as
when we were
5
solving
and 3. So 5 bits
complicated,
for the mantissa. So I'm
massive,
going to do
horrible
1.5
trigonometric
first. So let me
functions
just
and
put
we
my
were
number
trying to reduce
line.
them,
1, 2,
you could see what they were
half.
reducing to. So you weren't thinking about.
Right, I don't need to go
oh,
below
how
a
does
quarter.
that work? How does that work?
Okay,
You were like
so
going, oh, that's that.
1.5
that would take you
will
on a path.
be a 0
Right.
because it's positive.
So at the time,
One,
I thought she was
and
absolutely
then half.
crazy
So that's
and mean and
1.5.
horrible. But actually, she was doing us all a favour.
2.25. Again, it's positive. So I'm
Really
going to
was.
put 2.
She was
and
making us
then
precise.
2.5.
And that matters, and I think that helps me with my programming a little bit as well.
I want to normalise.
All right, so and that's one of
So
the
that's
things
the key
she
thing.
used to do.
So I'm going to have these
She was
normal.
quite happy to
so
do short form things.
for
if
this
they
one,
added clarity.
I've got 2
and
leading
reduced
zeros.
complexity.
So I
positive.
want to normalise.
I will
it.
write
I've got it over the
negative
top
with a
now.
minus v.
I'm going to normalise it to put the binary
So
point
instead
there.
of just putting a plus,
So
I'm making sure
1.5
I'm not
normalised is going to be 0, 1,
Right, so unsigned.
1, 0, and then remember
other
we
type of
had
integers have we got
the
then?
0. So that is
Yeah.
1.5
Okay. So we've got
normalised.
signed.
What would the exponent be? Yeah.
So
Positive
they
one.
are
So
negative
that's 1.5.
and positive.
The other one, oops,
Not at the same time, but we can
you didn't
represent.
register the control key there. Right, the
Okay.
other one,
Unfortunately, there are a
we need
number
to
of ways of doing
move
that.
the binary point twice this time.
We
So
have
we
to
need
know
move
about
it there
2.
and there. We've got to have the sign bit.
So for this, that splits.
So when we write this
or
one down, we've
forks
got 0,
into 2
1,
different formats.
0, 0.
So we've
1.
got
So if we had to move
sign of
that
magnitude,
another
which
place,
got
we'd have lost the fraction.
an hilarious
We'd have
couple
lost it. The
of,
precision was gone. What's the
letters
exponent this time?
representing it.
Yeah, 0, 1,
So get all the
2.
GIMP maths
So that
jokes
is
out the
2.25.
way
Both
now.
of them. Both
and
of them
2's
normalised.
complement.
So in general, in the exam, they're going to give you them normalised.
So you've got sine of magnitude
And just to
and
make
2's
it
complement.
harder. And they'll say, add these two numbers together.
So we have got
You
to
can't
learn
add them
about all
directly
these
together.
types. Sine of
We've got to
magnitude
have
is
the
just
same
mimicking
exponent, because the binary points currently exist
A
there,
human's
but
way
they're
of
not
writing
really
numbers.
there, are they? My feeling
for
on
the
this,
computer
you can do it several
process
ways.
sine
You
of
can
magnitude, it's got to
skew
do
them
work.
so they're in
It's
line
got
with
to do
each
more
other
work
and
than
then add
what we
them,
would.
or just unnormalise them completely.
2's complement
And add them.
is the computer
Okay.
way of storing
It's
integers
I don't care which method you do.
that the CPU
So
uses.
let's try and see if we can skew them. Let's try that
Easy
method
for the
first.
CPU.
So,
Unfortunately for us,
we want to make
it requires
both
us to do some work
the exponents
to
the
understand
same.
them. And this is
I don't
the
like this
standard trade-off in computer science. Anything that's easy for us is a nightmare for a computer to do.
This one
And anything that's easy for a computer to
This
do
one
is a nightmare for us to
is
do.
one bigger
And we
than that
can't
one.
get away from it. Okay?
Yep. So actually, we need to move the
Just
binary
the way
point
it
back
is.
a bit,
So
don't we? For that
the
one. To make it
terror
easier.
of the programmer
if I was to
is
do
that humans
that,
want everything to be as easy as possible.
I would have two
So
equivalent
what we've
numbers.
got to
They
do
both
is
have
try
an
and get the
exponent of
computer
one.
to do all the terrible
So-
hard stuff to present
So we
and
wanna make them
process
that.
in a format that's nice.
So the
for
first
us.
one doesn't need to change. So we're just going to write that
Where
one down.
we are with the
We're only
computers
bothered
now,
about the detail.
it's quite
part of the
interesting.
mantis.
So I've been
the
around
first one is
too
okay.
long.
This
So
one,
I've seen
we're going to
quite a
write
lot.
it down to always when you're
One
doing
of the
this bit,
things that
put the
you
binary
won't
point
have
in
ever come
place.
across
So we know
is
we've
writing
got a
programs
1
using
and a
this
0.
cast iron.
And then after the binary point, we've got a 0,
Punch
a
card
0,
right.
and a 1. We've got a
paper
mismatch.
card in it. This is before
It's
we
up
had
to you whether you
keyboard.
just automatically deal with that
Put
in
a
your
paper card
head.
in it. These really
But I
good. When
tend
they're
to
I need to
put
mend this,
the
when they're
zeros
working,
in.
you can have erasers underneath.
Okay.
Hold on.
Then, now that we've
Punch
got
holes
the
into
binary
card.
points balanced,
And then you put
we
those
can add up.
cards
And it is just addition.
into a computer that
Just like we
reads
did. So that's
where
no,
the light goes
1,
through the holes
1,
to see where you
1,
punched and
binary point,
converts it into
1,
text that is stored.
0.
Okay, so we've come from that.
If they want to know
And
what the
before
final
that,
answer is normalised,
we used to
then
have
okay,
a
we'll
system
normalise
where
it then.
you would
So
have
at the minute,
switches.
we've got to remember that
So
we've got an
let's say you had a
exponent of
computer
1.
that used
And
bytes
we're normalising
to
it, we're
store
going
its
that way, we're making it
instructions.
another bigger.
And
So
what it
our
would
final
do,
answer would be 0.1,
you would have 8 switches that
1,
you could flick
1,
on or off.
1. What
And
happens
if you've
to
been
this
to Fletcher
0?
Park, they've actually got one of the computers
Yeah.
that's
Drop,
set up
discard
like
it.
this.
We've only got space for 5
So
bits.
to program it,
Please
you went
don't
first
make
memory
that
location.
mistake. This one's
No,
got to
no,
get bigger,
one,
so
no,
it's
no,
going to
no.
be
Put the instruction in, press
that.
load.
So that's
Then it'd
one
move
way
on
of
to
doing it.
next
The other
memory
way is to
location, you go, no,
unnormalise, so you
no.
end
So
up with what
stand
we
there
start
flicking switches, loading a program.
But the key
one
bit,
byte
as long as
at
you
a
line the
time.
binary points up, then
Okay.
it is just arithmetic.
That's before we had stored program
Same for the
computers.
subtraction.
Colossus is a good example of that. They stored their programs
Okay.
on
Let's
paper
just
tape.
work it back to make sure we got
And
the
fed
right
the
answer.
paper
What did we
tape
say
in.
it was? 3. It
Not
should
the
be
robust
3.75, shouldn't it?
of things
Right,
to store
so-
programs on. To be fair, paper tape.
Whenever you're going back,
Something
we're right. We
like
know it's a
jams
positive
and tears
number,
and
so we haven't
rips.
got any messing about with two's complement to worry about
And then
on
we
the
moved
answers
on.
here. We look at this
Then
and we
we used
go,
to have
right,
teletype.
plus 2.
Didn't used to have screens.
Plus
used to
2
have
means make
typewriter,
this bigger.
connect to a computer.
So that means take the
Then
binary
we started
point that
getting
way. So
screens.
we're going to
Once
go
we started getting
1.
screens, that's when we started
2.
accelerating with computers.
So my binary point goes there.
Okay.
As soon as I
Keyboards.
do
Then
that,
we
I
started
can
getting
put the
different
column
input
in.
devices like
So we've got
mice.
1, 2,
So
4.
it's
We know
actually moved on
positive.
quite a
We've
way.
got half. and
The
we've got a
end
quarter.
goal is
So
to get
that's
to somewhere like
3.
Star Trek,
0.75,
where all you
which is what we
do
worked it
is
out
you
at.
talk to the computer. You don't even give it a very good
Right, I'll stop
explanation of what you
recording
want,
there.
and it somehow magically knows what you want. Okay, so you say, run a simulation of this and that, and the computer goes, yes, I will do that, or whatever the computer does, depends how it speaks, and then it'll give you the results in whatever format you want, just like that. That's where we want to get to. So the computer is doing all the work, and we're just being lazy. We're going to degenerate. It's going to be like Wall-E, where they're all sat talking to each other through a computer, even though they're sat side by side, engorging themselves. Hey, bring on the future. Anyway, right, I digress a little bit. Only a little bit, but I do digress. No, our standard problem is anything that's easy for a computer to do is difficult for us. Computer formats aren't designed for humans, they're designed for computers. Okay, so they take advantage of the way that computers work. Okay, so let's have a look at unsigned. So you've done this, you've been doing it at GCSE. We just didn't call it unsigned, we called it pure binary. For what? I don't know. Why we don't just call it unsigned numbers and let you know that. It's not like you, when you're doing biology, you call the heart the big thumpy thing, do you? The thumpy pumpy thing. Which actually would be quite a good way to call it. But there you go. Right, so unsigned numbers, only positive. So when we represent, so range of numbers, so they'll say how many different things can you represent, but they'll also say what's the range. Okay, so if we're doing, let's just do 4 bits. So you would need to know in an exam what the number format is. They'll have to say this represents an unsigned number. So we say 4 bits unsigned. So we go, okay, 4 bits. Let's not try and be clever about it. Let's put some column headings down. Right. So we know that we can represent. So if I do the next one along, we know we can represent 16 values with 4 bits. Yeah, everyone going to be happy with that. But what values? So the maximum and the minimum value. So if we've got only positive numbers, what's the minimum value going to be? 0. Even though 0 is neither positive or negative, but we'll come back to that. Right, so in binary, I would represent 0 like that. Everyone happy with that? Seen that a few times. What would be the maximum number then?
15.
Yeah, all 1. All the bits 1. So that represents 0. One other thing you've got to be careful when you're writing is zeros and O's and all that sort of thing. You've got to be very careful. You may find sometimes if you want to make sure clearly that something's a 0, you do that. A French 0 or continental 0. Right, so this represents 15. It's why I wrote the word 0 and not just put another O, because you would go, what's that? 15, right. That's easy, because I can easily add up 8, 4, 2 and 1 and get 15. What if I gave you a load more bits? What would be the technique? Yes, Ralph?
Look at the next column of -1.
Yeah. So when you want to do the range, you look at that column and you go, right, okay, 16 minus 1. That gives me 15. And what I will say to you, and I do this, when you're working things out and you want to like double check yourself and you can't remember how something works, think of a simple example. So if you say, right, okay, 3 bits, how would I do it? So I can do that quickly. I can say 3 bits, maximum number's that. Where did I get that from? Oh, that's 3, 4. It's that number minus 1. So you can always go back to a simple version of something. Okay? So that is your range. So what's peculiar about a range? What have you got to do if you get asked for a range? Just think in normal maths.
Biggest take by smallest.
No. If I was to say, what is the range, what would you write?
0 size.
Yeah. You don't put 15. You put the range is 1. There you go. Let's go. I was looking at Oliver. It's his fault. I'll blame you, Oliver. 0 to 15. Now I tend to not write it like that. I tend to do that. Right like that. 0 to 15. So that's 2 things they will ask you about a number of bits. How many values can you represent? And what's the range? Both can be worked out by going to the next column along. That's unsigned numbers in a nutshell. That's it. Not hard. You've been doing it. You've been doing it probably since year 7 because it's one of those easy little topics to give an easy win to students and everyone feels really good because they're clever because they know binary now. But they know it's pure binary. I know pure binary. And then you get all the other people going, pure binary, ah! It's unsigned numbers, you thicko. And things like that. But they don't say that to the faces. And the teachers don't say it to the face. No. Right, so that's unsigned. Let's have a look at these other 2 though. 2's complement and sign of magnitude. So let's do sign of magnitude first. Right, sign of magnitude. Mimicking how humans write it. So we literally have a sign and an amount. I'm going to do 8 bits. I'm going to scroll that over a bit as well. Right, now I said the bit on the right hand side was bit 0. It's got another name. Anyone know? Good, good. Least significant bit. Why is it called the least significant bit? I'll do a lot of whys on this course because that's what it's all about. Yeah, it represents the smallest value, doesn't it? That column. So it's the least. So if that changes, that's got least significance to the number value. It might actually have massive consequences depending on what the data is representing. But in terms of a number, yeah, it's only going to change the number by 1. The one on this side is called what then? Most significant. Because obviously if you change that one, the number's going to change by 128 in this case. So yeah, it's the most significant bit. When we're talking about signed numbers, it's got another name. It's called the sign bit. Because it represents the sign of the number. Okay, so let's just have a look at an example number. I'll do 2 numbers. I'll do them underneath each other. Right, 2 numbers. The only thing that's different is the sign. Okay? So it doesn't matter what format, there is a standard convention for whether a 0 or a 1 represents positive or negative. So in terms of our sign numbers, this, a 0, represents a positive number, and a 1 represents a negative number. Okay? So what are those 2 numbers? 97 and minus 97. But if I turn around and said, oh, actually they're unsigned binary, what's the first number? 97. What's the bottom one? Terrible number to add together. Yeah? 8 and 7 is going to end up being a 5, isn't it? So yeah, 225. This is it. This is data representation in a nutshell. We've got the same pattern of bits, but they mean actually different things. Okay? Now what's quite interesting is the positive version was the same as unsigned. Okay? So the way you work that out, that's simple. With the negative one, we just need to make sure that we only use this first bit column for the sign. It doesn't have anything to do with the value. Doesn't control magnitude. Can you see what a consequence we have with sign and magnitude? How many different values can we represent? I'm not asking about the range. How many values? Go on. 256. I can still represent 256 values. This is what I want you to get in your heads. The range and the values are different things. The range is what numbers are we representing. The values is just how many different bit patterns are there. That's all it is. Okay, so there's 256. Right, let's talk about the range then. So what's the biggest? 127. So if you got stuck, you know that if you're going to do a positive number, what you've got to do is put a 0. And then for the biggest, you're just going to say, right, I'm going to whack a load of 1s in there. And I'm going to add them all up. And that adds up to 127. But as Ralph said earlier, you don't need to do that. Look at the next column and take 1 away. Okay? Even I can take 1 away from a number. It's easy. The biggest negative value is going to be a 1 and all the 1s. Which isn't 255, it is minus 127. So the range with sign and magnitude is going to be, and you can write it however you want. You can, sometimes we write ranges like that, plus minus 127. Again, I still probably prefer to do that. What's weird, even though we're mimicking the way humans write numbers, we actually explicitly say it's either positive or negative because we're using a bit. Humans don't. Humans have implied positive numbers. So when I write this, say I'm going to pay you 672, I actually mean I'm going to give you plus 672. I'm not going to take it away. And we only tend to do that. Again, this is hilarious for computers to try and process numbers that you enter. Because it's like going, but I can actually, it's still legal to put that. So it's like, oh my God, you can put positive numbers in 2 formats when you're writing as a human. Great, brilliant. And you've got to deal with that on a computer. Okay, so that, I'm holding down control. Right, okay, there is a horrible side effect with sign of magnitude, which is probably, I think you were trying to guess. The reason, when you was coming out with some numbers, some of those numbers, I could understand why you were saying them. Let me ask you what this number is. So this is an 8-bit sign of magnitude. What number is that? -0, which makes literally no sense. This basically turns into, it depends how you then want to interpret it. Do you just say, oh, it's 0? Or do you make it an illegal number? Or pretend it's 0? The massive downside of this, so this is nice. This is really easy to write numbers down, but unfortunately, this thing now contains 2 pieces of information. We've got a sign information and we've got a size information. You can't use that easily and process it easily. You have to look at the 2 pieces of information before you decide what you do. So if you're going to add together, subtract, if you're going to divide numbers, okay? If you're going to start shifting numbers. So let's talk about that. If I've got this pattern of bits, I'm going to do a smaller number. I'm going to do a 4-bit number. So this is a 4-bit S&M number. Right, when you did pure binary at GCSE, I'm going to keep calling it pure binary now, and you did a shift, right, so if, let ignore what I've just written. If I shift that 1 position to the right, what would I get? There's a bit pattern. If I shift it that way, what would I get? What would I get? Yeah, excellent. You get that. If I initially had a sign of magnitude number, what have I done to that number? Oh my God, I've ruined it. What have I done? I've changed the sign. What was the thing that students who were going to do well on GCSE understood about shifting? What is the act of shifting? Yes, Ralph? Well, yeah, obviously, it affects the numbers. But what is that effect? Assuming this was just pure binary, what number is that first one? It's pure binary. Excellent, divide by 2. Yeah, that is an 8 and that's become 4. So as pure binary, it works, doesn't it? But if I then suddenly say to you, we're storing sign of magnitude, is there a strange man looking through the window, Oliver? Oh, he's trying to do it in a quiet way. He's doing it by hand instead of using a drill. So funny. Oh, that's all recorded now. Right. If we're talking sign of magnitude, how do I shift this without breaking it? So it was, well, in fact, that one's not going to work because that was -0. But what do you think I have got to do? So instead of just shifting it, which is like super quick, I can't just shift. What have I got to do? In order to preserve this, we'll do another number again in a sec. But what have I got to do? Let me give you another bit pattern. Let me give you another bit pattern. Right, so I'm going to do this. So this is a 5-bit S&M. And I want to shift it. So currently, what number is it? -4. If I shift it to the right, we're going to divide by 2, like you said. So it should be -2. What does -2 look like? Let's write it down, the answer. 1, 0, 0, 1, 0. So that's -2. So in order to shift this, someone see if they can work out a process.
You ignore the first one and then you shift it.
Nah.
No.
Yeah?
Shift it apart from one of the five.
No, you can't. You've got to shift the whole thing.
Shift it apart.
Right, so let's go through a step by step on this then. So we've got 1, 0, 1, 0, 0. Let's just try shifting it first. So I'm going to shift it. So I'm going to get, because we fill in the gaps with 0, don't we? Remember? I'm going to get that. I've now lost my sign bit. So before I shift it, what do you think I should do? And this is why sign of magnitude isn't used. What have I got to do? If I add the 1, so I've shifted it, if I do that, it's not the same number anymore, is it? That's now minus 10. So it's like, oh, that's not worse. It's getting worse. It's getting worse. So it's not that. I need to do this. Before I shift, what I need to do is preserve the sign bit. So copy the sign. So I say, oh, that was a 1. It was a 1. Then I can shift it. So I get 0, 1, which is still not right. I get that. And you think, oh, that's not going to work, is it? I need to get rid of this. Don't I? So I need to, like, sort of, whatever the sign bit was, I need to get rid of it. So that's not going to work. So so we've copied. So first step, copy the sign bit. So what I'm now going to do is I'm going to obliterate the sign bit. I'm going to get rid of it. Now, this is something that you've got to get good at doing. It's called masking. So I want to apply a mask. And we'll come back to this and we'll talk about it in more detail. But I just want to, I'm trying to show you why sign of magnitude is rubbish, basically. And it's not rubbish, but it involves a lot of work. And you can build circuits to do all this in one step and things like that. But I'm showing you the work involved. Right, to obliterate that, what I'm going to do is I'm going to say, I'm going to put my pen back on. I'm going to go 1, 0, 1, 0, 0. And I'm going to AND it with this. 0, 1, 1, 1, 1. So I'm going to perform, and this is just before we get going. So I've copied the sign bit. So I've got a copy, I've got to hold that. I'm going to mask it against this. So I'm going to perform AND, which you can all do. It's what we call a bitwise AND. So we go, 0 and 1 is no. 0 and 1 is no. 1 and 1, 0 and 1, 1 and 0 is not. So I've got rid of the sign bit. What we've actually got, when you apply an AND mask, you put a 1 where you want to preserve something and a 0 where you want to clear. It's a standard thing we use for clearing bits. Okay? And I'll show you lots of examples of that in actual program code. Right, now I've got that, I can shift it. So I can go, right, let's shift this right now. So I'm going to get 0, 0, 0, 1, 0. All looking good. But I've now got to put the sign bit back. So now I go, oh God, whatever the sign bit was, put that back. So I end up with 1, 0, 0, 1, 0, which is minus 2. Hooray! Got to the answer. All right, so sign of magnitude, great for us. Nice and easy. Hey, job done. Awful for the computer. Now, you can build circuits that will do that. So you try and shift a sign of magnitude number. You can build a circuit that does all those steps, sort of like in parallel. All right, just bang, just does it. But it's a lot of work. What I just did there was decomposition. Really low-level decomposition, which is what we've got to get good at. So eventually, I would like to be able to get to a point where I say to you something like that. I want to transform this pattern of bits to that. How would we go about it? And you'd be able to like break it down into like 4 or 5 steps. Okay. So sign of magnitude. Useful as an exercise. We do use it in some formats because it's used as part of floating point format. The real floating point format, not the one we're going to look at. Okay. But in general, not good for integer arithmetic. Okay, so we have another system called 2's complement.
And what that does, instead of the sign bit being a separate piece of information, it's combined with the number. Now this is really great for the computer, but it has a really big knock-on for us. It means when we're looking at certain numbers, we can't understand them. But we can use a process to help, which is a bit simpler than that. Okay, so let's have a look at 2's complement. So this is often written as 2C. So you'll see, because no one can be asked to say complement, I think is the problem. So you might see that, 2C, and I do it as well. 2's complement. So this again is a signed number format. And it is the standard way inside computers that we represent integers. So it's the standard way. Standard format for signed integers. Which we sometimes shorten to ints. Okay, so let's go with, we're going to go with an 8-bit number here. How many different values can we represent? 256. Good, good. Right. It has the same makeup. I'm going backwards there. I'm going back. I don't know, Back to the Future or something. I don't know. Terrible film. Everyone keeps going about how great a film it was. Everyone keeps going about how great Cobra Kai is, because wasn't the Karate Kid really good? No, it wasn't. It was awful. I lived in the 80s. It was awful at the time. Don't know what you're going on about. Back to the Future was a terrible film. There's all this like 80s retro introspection rubbish going on. Yeah, and people are saying how great it was, and you think, oh, I don't remember it that way, but go on then. Right, this is still the sign bit. This is important. So when we're looking at either sign of magnitude or 2's complement, we can look at it and it uses the same format. A 0 means positive. A 1 means negative. So when we're writing numbers in 2's complement, our first thing is to say, what number are we writing down? Is it positive or negative? So let's have a look at a positive number. Positive 33. If it's positive, everything is exactly the same as everything else. We write down a 0. We go 0, positive. So we put the sign bit in. And then we go, right, whatever we've got left, let's try and make 33 up. So we won't get a 64, we'll have a 32, none of the others. Get a 1. So hey, that's plus 33. So that's identical to sign of magnitude. Whenever you're doing signed numbers, you're always thinking about the sign bit first. I don't know why I'm doing that. That doesn't mean sign bit. Right, the trick becomes when we get to put a negative number. Now, our brain should straight away go, right, okay, what are we doing? We're doing 2's complement. Right, positive numbers, they're fine. I just write down sign bit of 0, write it down. When I've got a negative number, I've got to go, no, 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 I don't know how to do it. I don't know how to do it. Okay, you can look this up. I could teach you it, but I'm not going to teach you it. I can do it, but I'm not going to teach you it because it's complicated and confusing. You can write numbers straight down into 2's complement, but we're not going to try. We're going to do the method that the CPU would use. If we want to write down a negative number, we have to stop and say to ourselves, I can't do it. But what I can do is I can write down the positive version of that number. So I'm going to write down 33, which I've actually just written, which makes it even easier. You'll often find that they do that in the exam. They'll get you to write a number down and then say, what is it in 2's complement? And you go, fair enough. Right, so I write down a positive number, because I can. Because I know how to do it. Sign bit of 0, that's a positive number. And then what I do is I perform a process which is called 2's complement. So the storage format is called 2's complement, and the process of dealing with these numbers is called 2's complement. What effectively I am going to do is I am going to multiply by minus 1. So I'm not going to change the magnitude of the number, but I'm going to change its sign. -1 is a cool thing because the CPU will have an instruction that does this. It'll just go bang. I can do that. Right. This process is described as flipping all the bits and adding 1. Okay? But there is a quick way of doing this. So you do one step. So what we're going to do is flip all the bits. We're going to go flip, flip. Try not to say Philip, which is what I always try and say. I don't, because my mouth goes all dry and I start saying Philip. So Philip, 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 and then you get to the very last one and you change it to a 1. That is what -33 looks like in 2's complement. We'll do a lot more of this, so don't worry that we're getting towards the end of the lesson. Okay? And you can see just by looking at it that it doesn't look like -33 in sign of magnitude. There's loads of 1s everywhere. It's like, whoa, what's going on? But actually it is -33. Okay? To prove it, we're going to add them together. What should we get if we add 33 and -33? 0. Let's do it. You're all experts at adding binary, pure binary. Right, 1 and 1 is 0 carry 1. 0, 1 and 1 is 0, 1 and 1. 0, 1 and 1. Oh, didn't do that. Say I get ahead of myself. That's 0 carry 1. Oh, that was handy. 0 carry 1. 0 carry 1. 0 carry 1. Always box off the carry and label it carry. That's a special bit in the CPU. But we were dealing with 8-bit numbers. The 8 bits we've got are 0. I didn't look at the sign. I just treated it as an integer. I went, it's an integer, it's in 2's complement. Hey, it just works. So what you've got to do, if you get given something, so let's just do another one. So let's do, I don't know, 48. So let's write down 48. Positive 48. So this is 2's complement, but I've written down 48. And I want to write down -48. So I'm going to take 48 positive and I'm just going to flip and add. So I'm going to go flip, flip, flip. I've got to the last one. So I just say I'll write it down as a 1. What have I not done? Everyone just let me do that. I went flip, flip, flip. What have I done? I didn't flip that one, did I? So what I'm not going to do is that. In the exam, if I do that and I go, oh, buggered it up, I'm going to go like that. I've got a whiteboard, so I don't have to. Something like that. Flip. When I get to the last one, leave it as a 1. Because it's the last one, everything else is going to be a 0. If it isn't a 0, everything else, it ain't the last one. All right? So you can double check yourself. Oh, no, I'm going a bit stupid here. So everything else, you write down as 0. So that is -48 in 2's complement. Try and get into a habit of writing down next to what the number was. Because you need to make sure that the examiner knows that you didn't think that was the answer and that the answer is the final bit. And then my dear old maths teacher would have forced me to do that with a ruler. I'd have been shot down in flames for doing that. I could have used a ruler, but... Right. So the process is simple. So if I then get a number that is already in this format, so let's say I add this number, and I tell you that's 2's complement, what can you tell me about that number? It's positive. That's where you start. I'm doing that again. That's gonna be sign bit for me. I might put it on a t-shirt, sign bit. That'd be quite funny actually. Always look at the sign bit. If you've been told it's 2's complement, But look at the sign bit first. If it's positive, you go easy peasy, read it out. So what number is that? Plus 64. Okay, excellent, easy. So actually, sign of magnitude and 2's complement, the positive numbers are the same. So just look at it, it can't tell you what the format is. Okay, now, if I get this, and I tell you that's 2's complement, what have you got to say to yourself? No, you haven't. You've got to say, no, I can't do it. It's negative. You've got to say that. You can't just say negative. You've got to tell yourself you can't do it. That's the key. So you go, right, okay, I don't know what that is. But I know a process called 2's complement that will give me the positive version. So it'll turn a positive number negative and a negative number positive. So I just go flip and add then. So let's do flip, 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 flip. I've got to the last one, which just so it happens to be the last bit as well, leave it as a 1. So actually, that number is minus, because it was negative to start with, 5. So it's actually easy, but like everything that we're going to do for the next 2 years, I don't want you to remember how to do it, I want you to remember the process. Everything for me in computer science is a process. Processes can be learned, they don't have to be remembered. If they had to be remembered, I wouldn't know any of this stuff. When I was doing my master's degree exams in signal processing and artificial intelligence, I had to do a quadruple integral calculation because it was to set attenuation for an antenna for a satellite receiver. The question was about, great question. And I couldn't remember, when you've got a triangle, which one's sine and which one's cos. I couldn't remember. I had to go from first principles. This is on a question that's way more complicated than this, but I got stuck with this. Couldn't remember sine and cos, which way round they were. So you've got opposite, adjacent, but I couldn't remember whether sine were, and I can't remember now. Is it opposite over hypotenuse? Yeah. I couldn't remember that. So in my super really nerdy maths, terrible maths paper, I had this diagram. And I actually couldn't remember it. So what I ended up doing was well, I know that root 2 is bigger for sine than it is for cos. And I did it like that, which is a real weird way of doing it. But that gave me, and I could answer the question then. But it was like, oh man, they're going to laugh when they see that. I don't care. We don't care whether they think we're a dumbass as long as we get the right answer. Okay? Right, so just to sum up, data representation is all about understanding that the bit is just a value. Those values mean nothing. They don't mean anything until we say what they represent. And we can make our own formats up for everything. Okay? These are just standard formats. We can make our own. If you're doing something weird, you might make up your own format and use it to represent whatever it is you're representing. Okay, so